A piece of old steel can look completely ordinary. Rust on the edge, salt in the cracks, maybe a number stamped into it that nobody cares about anymore. But for a while, certain scientists and engineers looked at metal like that and saw something rare. Not gold, not a lost weapon, just steel made before the world learned how to throw nuclear fire into the sky. That is the odd part. In some very specific uses, steel made before the first atomic explosions could be more desirable than newer steel. Not because newer steel was dangerous to touch. Not because cars and bridges became radioactive traps. For normal life, this difference is basically meaningless. You could walk past modern steel all day and never notice anything. But a machine built to hear almost nothing can be disturbed by almost anything. The name for this material is low background steel. It is also sometimes called pre-atomic steel or pre-war steel. The phrase sounds like something from a conspiracy forum, but the idea is real. It belongs to a world of laboratories, particle detectors, radiation counters, and experiments where the signal you want is so weak that the materials around the detector become part of the problem. Start with background radiation. It is always there. Cosmic rays come from space. Rocks and soil contain naturally radioactive elements. Concrete can have a tiny signal. Bananas contain potassium, and a small fraction of potassium is naturally radioactive. That does not make bananas scary. It just means the universe is not silent. Now imagine a detector that is not looking for a loud event. It is not measuring a reactor accident or a glowing piece of uranium ore. It is trying to count rare decays, faint particles, or tiny traces of contamination in a human body or a sample. In that setting, the detector needs quiet surroundings. The room matters. The shielding matters. Even the metal box around the instrument matters. A normal person would call it clean metal. A detector might disagree. The atomic age changed the background of the planet in a small but measurable way. The first nuclear explosion happened in 1945. After that, especially during the decades of atmospheric nuclear testing, radioactive material from detonations was carried upward, spread by winds, and slowly returned as fallout. For everyday life, the amounts became very small over time, especially after major limits on atmospheric testing. Scientific instruments are different. Steel is where the story becomes awkward. For a long time, making steel involved exposing molten metal to air, oxygen, industrial gases, scrap, and equipment from a messy, real-world supply chain. If trace radioactive isotopes were present in that environment, or if a contaminated source accidentally entered scrap metal, some of that contamination could end up in the finished steel. Cobalt-60 is one isotope people often mention in this context. Iron and steel are not naturally radioactive in the scary sense, but contaminated steel can carry a weak radioactive signature. That sounds minor, but it matters. A Geiger counter, or a radiation detector, is supposed to detect radiation from outside itself. If its own steel casing contributes a tiny background signal, the measurement gets noisier. It is a bit like trying to record a whisper while your laptop fan is running. The fan is not loud enough to ruin your life. It is just loud enough to ruin that recording. So engineers began to care about a strange question. When was this steel made? Steel made before the first nuclear weapons tests had avoided that global layer of artificial fallout. It was not magically pure. It could still contain natural impurities, and every batch still had to be tested. But it had one attractive feature. It came from before the bomb pulse entered modern industrial materials. This is why old ships and shipwrecks became part of the story. A ship built before the nuclear age could contain tons of steel made in a world that had not yet been dusted by atmospheric nuclear testing. Some of the most repeated examples involve old naval wrecks, including ships associated with Scapa Flow in Scotland, where parts of the German fleet were scuttled after the First World War. The image is almost too cinematic. Scientists needing metal from dead warships so they can build instruments quiet enough to study invisible particles. But this is also where the internet version often gets too neat. It was not that every pre-1945 ship became a priceless scientific treasure. It was not that every old bolt was worth a fortune. Salvage is complicated. Legal protection matters, corrosion matters, and not all old steel is useful. A rusty plate from a wreck is not automatically laboratory-grade material. Someone still has to know its history, cut it, test it, certify it, and decide whether it is worth using. The value was niche. That is the word that keeps this story honest. Low background steel mattered most for equipment where every little count on a detector could confuse the result. Whole body counters, for example, are machines designed to measure very small amounts of radioactive material inside a person. Particle physics experiments and rare event searches have similar problems. If the shield around the detector is noisy, it can imitate or cover the thing you are trying to find. In ordinary construction, none of this matters. A bridge does not care. A kitchen sink does not care. Your bicycle frame does not care. The difference is below anything that would make sense for normal use. This is not a story about poisoned modern steel. It is a story about instruments so sensitive that normal materials become too loud. A dark matter lab has a boring shopping list that gets weird fast. Copper, steel, lead, plastics, cables, screws, seals. Each item might need to be screened for radioactivity. The experiment may be placed deep underground, not because scientists enjoy working in tunnels, but because rock blocks much of the cosmic radiation raining down from above. Then they add shielding. Then they choose cleaner materials. Then they worry about radon gas sneaking into the detector area. And yes, this gets messy fast. Modern experiments do not simply grab random old steel and hope. Some use specially produced, low radioactivity stainless steel, high purity copper, carefully selected lead, or other screened materials. For example, dark matter and neutrino experiments have published work on custom low background stainless steel and on measuring radioactivity in candidate materials. The point is not nostalgia for old metal. The point is control. There is another metal with an even better story. Ancient lead. Freshly refined lead can contain lead-210, a radioactive isotope in the uranium decay chain. Lead-210 has a half-life of about 22 years, which means its activity drops significantly over decades and centuries. So lead that was smelted long ago, then sat undisturbed for hundreds or even thousands of years, can be unusually quiet. Roman lead ingots, ancient shipwreck lead, and old archaeological lead have all been discussed in connection with shielding for ultra-sensitive experiments. That creates a genuinely uncomfortable conflict. To a physicist, a lump of ancient lead might be a wonderful shield. To an archaeologist, it might be a piece of history that should not be melted or hidden in a laboratory wall. The same object can be both a scientific material and cultural heritage. One person sees silence. Another sees a Roman mine, a trade route, a wreck, a date, a story. This is where the idea becomes larger than steel. The atomic age did not just create weapons and reactors. It left signatures. Some are obvious, like test sites and political treaties. Some are invisible until an instrument looks closely. In carbon dating, for example, scientists also have to think about changes caused by nuclear testing and fossil fuels. Different problem, different material, same basic lesson. Industrial history can become part of the measurement. It is tempting to turn this into a simple before and after myth. Before 1945, clean. After 1945, contaminated. Nice story. Too nice. Natural radioactivity existed long before humans built bombs. Modern material production can be controlled. Some old materials are useless. Some new materials are excellent. And the most sensitive laboratories do not rely on vibes. They measure the radioactivity of the actual material they plan to use. Still, the boundary is real enough to feel strange. There was a time when steel did not carry that particular modern fingerprint. Then the atmosphere was used as a testing ground, and tiny traces of that decision entered the global background. Most people never had to care. A detector did. There is a small practical detail here that makes the story feel less like science fiction. If you build an ordinary tool, you mostly ask whether the metal is strong, cheap, workable, and resistant to corrosion. If you build a low background detector, you may ask whether a component gives off a few extra counts per day, not per second, per day. A screw, a weld, a plate, a cable tie. The boring parts start to matter. That is why the old metal story survived. It takes a giant historical event, nuclear testing, and connects it to something humble, a sheet of steel. It shows that the world does not reset after a technological leap. It absorbs the leap. It mixes it into air, supply chains, measurement standards, and junkyards. The strangest part is not that old steel was sometimes valuable. The strangest part is that metal can have a kind of historical timestamp. A plate made before the bomb and a plate made after the bomb may look the same, weigh the same, and hold the same bolt. But in a quiet enough room, with a sensitive enough detector, one of them may carry less of the 20th century inside it. And that is a very odd thing to realize. We usually imagine history as something written in documents, monuments, and photographs. Sometimes it is also written in materials, not in a dramatic way, not with glowing metal or movie radiation, just a faint background, small enough to ignore, but real enough that scientists once went looking for steel from a world before the sky was used for nuclear tests.
Thanks for watching! If you enjoyed the video, please like, subscribe, and leave a comment below. See you in the next one!